We propose a method for planning sequences of actions based on user demonstrations in the context of symbolic planning. Continuous trajectories connect different symbolic states, but the continuous positions chosen as a result of each of those trajectories will affect the execution of future trajectories. We learn models over which features we expect to see in a successful instance of a particular action, and we use those to do our planning. First, we sample out the next available actions. Then, we sample from the set of possible end states to choose where the next actions after that will take place. We can continue this until the task is accomplished and we arrive in the symbolic goal state. We can then refine our search based on the probabilities of the trajectories that we sampled, instead moving into higher probability states and choosing better trajectories iteratively until we can accomplish our task in a new environment. We performed experiments both in simulation and on a physical robot. In simulation, we trained a simple assembly task by having a user teleoperate a simulated Barrett Wham arm with a pair of Razor Hydras. In this magnetic assembly task, each of our pieces has around a centimeter of give before they'll snap together. This means that we want to get our margin of error down below that threshold. We compare our method to the simple case where each action is produced on its own. While for many simple actions this works well, for more complicated procedures this will run into problems. For example, when trying to connect this link piece with a node, we'll run into failures when we see that the align action does not know to line up perfectly with the mate position. To achieve the best results in this situation, we want an algorithm that can actually look ahead and see where the robot will end up after each of its actions and how that relates to the future. Our full algorithm does this. We sample trajectories corresponding to the first action, then we sample trajectories corresponding to the next couple possible actions after that, and so on until we arrive in our goal state. We can then update distributions corresponding to each of these to do our trajectory search and to adapt to new environments. After the grasp action, we find that the link may have shifted in unpredictable ways, so we replan afterwards using the new correct position of the link in the hand. Part of being able to adapt is being able to avoid obstacles. In this case, the robot prefers to grab the link from the right and then attach it to this other node. When we move the obstacle a little bit, that's no longer an option, and our approach is able to adjust. We then trained our universal robot UR5 to perform the same task. We used computer vision to find links and nodes in the new environment. The AR tags in these videos just represent the table. The algorithm was able to choose a link or a node based on whether or not it would get a better grasp picking that particular object. Here we can see a case where the robot chose to grab the node instead of the links. The robot will choose a node over a link based on which face presents itself and whether or not feasible grasps are available for each of the two pieces. It may also choose one grasp over another if there are obstacles blocking one particular necessary approach or other movement. We believe our algorithm has huge potential to allow robots to plan complex multi-step procedures where the effects of every action determine the success of future actions. In addition, our approach allows our robots to adapt to new environments and to avoid obstacles. In the future, we would like to do more experiments with more complicated robot tasks.